Hello everyone. Today we're gonna discuss a project called Spegel. I'm not sure if I'm pronouncing it correctly or not. It's a Swedish name. Spiegel describes itself as a mirror. Uh, it is a mirror in Swedish, but it's used as a mirror for images so that when new nodes want to pull an image that is located inside the Kubernetes cluster, it doesn't have to go to the external registry. It can just request it from the other nodes that has these images. So let's decipher the description here. It's called stateless, which means Spagel doesn't save any image itself, but it uses container D's store to serve the images or save the images. And it's OCI compliant. OCI stands for Open Container Initiative. So it's compliant with the specifications. So it can be a, uh drop-in replacement to any other registry, and it would be used as a mirror so that it is acts like a middleman between the node that is requesting the image and the external registry. So this is a nice GIF. I try to use this extension so that I can stop it and explain to you what's happening because it's moving so fast. So here we have node 5. It's trying to pull an image. It's gonna first check within the cluster. We have here 8 nodes, and the result is that the image is not in the cluster. How it knows that is through a peer-to-peer network that uses a distributed hash table, and we're gonna discuss that later in the video. So follow with me now. So the image is not in the local cluster. It's gonna go all back to the external registry, get the image, store the get. In this case, the image has 3 layers. Uh, the image layers are variable depending on your image, and then it's gonna store it locally in the container D content store, or depending on the container time that you're using, it might differ. So node 5 now have the images and its layers stored. Node 3 wants the same image. It's gonna look in the cluster through the peer-to-peer network. Node 5 already have the image, so it's just gonna request it from node 5, get the layers, store it locally, so on. Node 1 and 2 wants to pull an image. They're going to look up which nodes on the cluster have these images. Node 3 and node 5 have them. So they're going to send the requests to the layers. And notice something here, that the layers doesn't have to be going to the same node, uh, because the images are divided into layers, and uh, normally when you pull a request even from external registry, it works on a layer level. So yeah, that's an overview on Spegel. I created some diagrams that dives into the internals of Spegel. It helps you visualize how different components interact. So first, an overall high-level architecture. So this is the your Kubernetes cluster. It has 3 nodes in this example. Uh, Spiegel works is deployed as a daemon set, and a daemon set means that each pod would run on um, not each pod. So daemon set means that you would deploy each pod of the daemon set on every node, and it's usually used for monitoring and stuff. But Spiegel uses daemon set here so that you have a Spiegel registry running on every pod, running on every node. Sorry for the confusion here. So it's a Spiegel pod running on every node. Then you have container D, which is your container runtime, and that has to exist on every node. Container D is the one that's responsible for the container lifecycle. It would request the image from the Spiegel pod first, because Spiegel pod is acting as a mirror. Spiegel would check locally if the image is there, is gonna respond with it. If not, it's gonna interact through this peer-to-peer network that you can see. Each pod is interacting with each other through this network. In case the image is not present locally, container D would fall back into the external registry. So this is a high level overview. Next, we have a deep dive into the Spiegel pod. So, Spiegel pod here was a black box. These are the components inside the Spiegel pod. First, we have the container D client, which is the client interacting with the container D uh, component. Here it's interacting with the daemon, which is the engine that is the main component of the container D that is moving things and controlling stuff. And this daemon is interacting with the content store, and you can think about it as files stored in your local file system on the nodes. The container D client in the Spiegel pod interacts with the state tracker, which keeps track of everything so that it can update the Prometheus metrics, which will help you visualize the Spiegel status in your deployment, and would also update the peer-to-peer router. So through the peer-to-peer router, it would gonna update the distributed hash table. And distributed hash table, you can think of it as a data store that tells you which node has which layers, so that you can look up uh, the peer-to-peer router to know this information when you're pulling new images. And then you have Bootstrapper, which helps new nodes join the peer-to-peer network. And then you have an HTTP server version 2, so that you can in parallel serve the image layers to the requesting nodes. So this is a deep dive into the Spiegel bot. For the metrics, I created this Grafana dashboard. It's currently still in the pull request. Hopefully, it's gonna be merged into the project. But you get things visualized as number of requests, the mirror requests, how long it takes for Spiegel to know which other peers have the image layers, if it exists locally in the cluster, and other useful stuff. So I hopefully by the time you watch the video, the dashboard gets merged into the main, and then you can use it. If not, you can just check this pull request and get the Grafana dashboard. It should work outside of the box with your Prometheus input data source. So moving on, the most important diagram in my point of view, which is image pull flow. You have your container D pulling the image. Is gonna first interact with the speaker registry as it acts as the mirror. Here we're requesting a manifest. So in that case, Spiegel would try to see resolve means it's trying to see which nodes has which layers. If there is a peer returned from the peer-to-peer router, it's gonna request format, get back the content streamed, and save it inside the content store, which means it saves it locally inside the node uh, storage in the container D content addressable store. If not, it's just gonna get a 404 and request it from the external registry and also save it. So in both cases, it saves it so that in the future it can be reused locally and it can be advertised and shared to new nodes joining and requesting the same image. Then you have the peer-to-peer network formation diagram, which means how the peer-to-peer network is formed, and this is using Kubernetes leader election process. So if you have 3 nodes in the cluster, each would participate in the election. The first node that acquires the lease would become the reader. Other nodes would gonna discover this node, and then the node would share with every node. The leader node would share what are the peer lists that we have within the cluster. Here, this is the default values for the leader election process. The lease duration is 10 seconds, and it has to be renewed every 5 seconds. Every 10 seconds. If the lease is not updated within 5 seconds, another node can become a leader, and each node retries um, connecting to the leader election process, or retries acquiring the lease every 2 seconds. These are just default values in that case. Moving on, state tracking and content advertisement. The state tracker component that we discussed keeps asking container D for images to check which images is stored locally on the node, and it advertises it to the peer-to-peer through the peer-to-peer router to the distributed hash table, so that other nodes know which nodes has which layers, and it's gonna update the matrix to the Prometheus matrix so that we can do the dashboarding and stuff. So that is happening like every 10 minutes. But in case there is an image deletion or image update or create, this is gonna be sent to the state tracker, which on which does the advertisement. Once it gets this update, it doesn't wait the full 10 minutes. So that happens um, directly once an update happens. It also updates the metrics. Moving on, the content resolution process, how we get the content or the image layers. First, we ask the peer-to-peer router. Peer-to-peer peer-to-peer router would tell us which peers have this content. It can be a manifest or an image layer that we're looking for. It's gonna try the first peer. If first peer fails, it's gonna go to the second peer. If second peer fails, it's gonna fall back to the upstream registry. Moving on, how data flows through the Spegel deployment. The state tracker keeps updating the peer-to-peer network as we discussed before. The peer-to-peer network advertises to the distributed hash table and asks the distributed hash table in case it wants to see which node has which layers. Then we have the content path. Container D is the one that pulls the images. It sends the request first to Spiegel as we discussed. If Spiegel doesn't have it, gonna check it appears. If it's not in the local Kubernetes cluster, it's gonna fall back to the external registry. The failure scenarios that can happen if there is no peer, which means the image is not stored locally inside the cluster, we're gonna fall back to the external registry. In case a peer connection failed, we're gonna try an alternative peer. If the content is corrupted, which means that the image is corrupted inside the cluster, we're gonna fall back to the external registry. Finally, the matrix that we have is the ones that I shared here somewhere. Yeah, these are the ones, and you can see them here. Total number of mirror requests, resolve duration, the request latency, and stuff, other stuff. And these are the sources of these metrics. Yeah, I hope I didn't take a lot of time, but hopefully I benefit you in that uh, explanation. Thank you, and see you in the next video.